Hello, welcome to this fifth session on this fluid dynamics. If I am right, this is my sixth session. I mentioned my email address and mobile number in this slide. I want feedback from your side. If any one of you have any doubts as far as the fluid dynamics, what I taught you till now, you are most welcome to write an email to me. Probably within next couple of minutes you are going to get a response from my side. I try to cover all types of problems, whatever the type of problems you can expect in the examination, and also whatever the basics you need in order to solve those problems. So I covered everything keeping the syllabus in mind. If you still have any doubts, okay, you are welcome to write an email or you can call me on this number. With that, let us see what we studied in the last class. A quick recap of what we studied in the last class. We started with the orifice meter problems. We started with a couple of problems, different types of problems on our orifice meter. We started with pitot tube. We started with where we are going to use this pitot tube, what is the principle on which this pitot tube works, and what is the equation for velocity. So this we discussed in the last class, and also along with that we also studied about this pitot static tube, which measures both static pressure and stagnation pressure. We solved a problem on that. Then we started with this momentum principle. Then we started with this force exerted by water on a bent pipe, and we solved a couple of problems on that. Then we started with this vortex flow. So we defined two types of vortex flow. One is a free vortex, the other one is a forced vortex. So I said how we define this free vortex and forced vortex. In case of a free vortex, so no external torque is required to rotate the mass, whereas in case of a forced vortex you are going to apply some external or mechanical force in order to rotate the mass about its mass center. Then we showed that the relation between velocity and radius in case of a free vortex, that is Vr is equal to constant. Then I also mentioned about couple of examples where you are going to see this free vortex flow. So free vortex flow is very common in case of river flow. If you go to any river, if you stand on one bank and if you just closely observe the flow of water, you are going to see number of wheels on the river. Especially when the river is turbulent, you are going to see this wheel pools in a river. That is one example I gave. The next simple example I gave is this tornadoes, formation of tornadoes and then cyclones. That's about this free vortex. Then we defined forced vortex. So the example I gave for this forced vortex is, I gave a simple example. I asked those who have not experienced with that, take a bucket full of water, then before start rotating the water with a stick, the water level in the bucket at the free surface is almost horizontal. Place a stick at the center of the bucket, start rotating the stick either clockwise or anti-clockwise. So after some time you are going to see a different profile. In other words, the flow, the level of water is not constant. At the center of the stick or eye of the stick, the level of water is less, whereas at the edge of the bucket you are going to see the level is much high compared to its original level. That is one classic example for this vortex flow. I also mentioned about this vortex flow is extensively used in the design of pumps and turbines. I said this pumps and turbines you are going to study in the next semester. Now we now to derive an equation or a relation between this velocity and radius. So let us see how to go about that. This is the point where we stopped in the class last class. Let us continue from that point. So please look into this figure. In order to derive an equation or a relation between this velocity and radius, I consider a fluid in a container, okay, and this is the angular velocity, okay. Now I consider two fluid particles. So particle 1 and particle 2, these two are represented as 1 and 2, and this particle 1 is at a radius of r1 from the center of the axis or the high of the axis, and particle 2 is at a distance of r2 from the radius of the axis. Now with this, let us see how to derive an equation for this relation. So let us start with this. The fluid mass in the forced vortex flow rotates at a constant angular velocity omega. That's what I showed here. If you look at this figure, I showed this constant angular velocity as omega. The tangential velocity of any fluid for particle is given by, so this is V is equal to omega into R. Okay. Now kindly recall, these are the formulae you studied in your high school and PU. Okay. Again I repeat, the tangential velocity and the angular velocity are related as tangential velocity V is equal to angular velocity into its distance from the center of the axis or the eye of the shaft, where R is the radius of the fluid particle from the axis of rotation. That is what I mentioned here. Suppose, for example, if you talk about point 1, this radius is R1. Suppose if you talk about point 2, it will be R2. Hence, angular velocity omega is given by omega is equal to, just rearrange this equation. I am looking for this value of omega. Omega is equal to tangential velocity divided by R. That is equal to constant. Now, variation of pressure of a rotating fluid in any plane is given by, I repeat, the variation of pressure of a rotating fluid in any plane is given by, kindly remember this formula, because this derivation is quite complex and it is not there in your syllabus. That is the reason I put directly this equation. Again I request you, kindly remember this formula. This dP is equal to rho into omega square R square divided by R into dr minus rho g into dz. Now integrating the above equation for points 1 and 2, okay. So you are going to integrate this equation between these limits 1 and 2. You are going to get this integration of this dP is equal to integration of this whole equation. Now again I repeat, the limits are 1 here and 2 here. Now on simplification, okay, this becomes my capital Z is equal to Z2 minus Z1, that is equal to V square by 2G, that is equal to omega square R2 square divided by 2G. Now don't be panic, I skipped a couple of steps here. Again I repeat, so from this integration point onwards, I skipped couple of steps here. Absolutely don't be panic. Okay, basically what right now I am looking at is, I am looking for this simplified form of this equation. Okay, so I expect you to write this equation, then on simplification, so this Z is equal to Z2 minus Z1 is equal to V2 square by 2G is equal to omega square R2 square divided by 2G. Now whenever you have time, if you simplify this, you are going to get this equation. Okay. Now what are the type of problems we are going to solve on this force vortex flow? We need this equation. Okay. So that is V2 square by 2G is equal to omega square R2 square divided by 2G. Is it clear? Now, so what I said, you need to remember this relation between tangential velocity and angular velocity. Tangential velocity is equal to angular velocity into R. So from this, find the equation for this angular velocity. Angular velocity is equal to tangential velocity divided by R, that is equal to constant. Now I said this derivation is not there in your syllabus. Kindly remember this equation. This dP is equal to rho into this equation. Now integrating the above equation between these limits, that is the lower limit is 1, the upper limit is 2. If you integrate this between R2 and R1, you are going to get an equation on simplification, that is Z is equal to V2 square divided by 2G minus omega square R2 square divided by 2G. Now this is what I mentioned here. Remember, in case of a free vortex, we know that external force is not required to rotate the fluid mass, whereas in case of a force vortex, you require some external force or mechanical force in order to rotate the fluid mass. The same thing is represented here. Look at that. In case of a free vortex, the peripheral speed is inversely proportional to the radius. Again I repeat, the peripheral speed is inversely proportional to the radius in case of a free vortex. In case of a force vortex, peripheral speed is proportional to the radius. Now look at this. So VR is equal to constant. This we showed it in the last class. Now V is proportional to 1 over R. Okay, this is the relation between velocity and radius in case of a free vortex, and in case of a forced vortex, this v is equal to kindly make it as omega. So tangential velocity is equal to angular velocity, okay, into r. Okay, so tangential velocity is equal to omega into r. Kindly this and this is same, so v is equal to omega into r. I think with that theory, what I presented is more than enough to solve a problem. Let us see one or two problems. So then you will get an idea what type of problems you are going to expect and what are the formulae you need to require in order to solve these problems on this free vortex and forced vortex. Now just now I said one example, kindly recall that. I gave an example of bucket. Okay, so if you start stirring the water with a stick at the center, okay, I said before start stirring the water, the level of water in the bucket is OO. Once you start stirring this water with a stick, after some time, the green line what you are seeing in this figure is a profile. I said, if you recall, I said at the center of the stick or at the eye of the stick, the water level falls down, whereas at the edges it is much above the normal level. So this is the form of a parabola. Okay. Now with this background, let us see what the problem says. Prove that in case of a forced vortex, the rise of liquid level at the ends, I am talking about this OB is the rise of liquid level, is equal to fall of liquid level at the axis of rotation. What is the fall of liquid level? So liquid level, I said initially before start stirring the stick, the level of water is at this OO. Now at the center you have a fall of OA, and at the ends there is a rise of OB. Now what is required? We need to show that this OB is equal to OA, right? So then the next question is, sir, why do we need this? So we need this relation once we start solving the problems. Let us see how to show that this OA is equal to OB. Now look at this. This I call this as capital R. That is from the center of shaft to the end of the container. I call this as capital R, the radius of the container. Then this fall in level I call it as X, the rise in level I call it as Y, and from A to the bottom I represent this as small h. That is what I mentioned here. Let R, radius of the cylinder, OO, initial level, the level of liquid in the cylinder when the cylinder is not rotating. Okay, again I repeat, I said several times this OO is the initial level before starts rotating the cylinder. Now initial height of liquid, remember this is the initial height. Now from this figure, what is this initial height? Initial height is this height plus this height, that is h plus x. That is what I mentioned here. So initial height of liquid in the cylinder is h plus x. Now corresponding to this h plus x or initial height, what is the volume of liquid present in the cylinder? That is given by pi r square into the vertical height. The vertical height is h plus x. So call this as equation number 1. Again I repeat, okay, let OO is the depth of water or depth of fluid present in the cylinder before start rotating the cylinder. Now this height of this fluid is given by this h plus x. Corresponding to this OO, what is the volume of the cylinder, volume of the fluid? Volume of the fluid corresponding to this is given by pi r square into this vertical height, that is h plus x. That I called that as equation as first equation. Then let the cylinder is rotated at a constant angular velocity omega. Now you start rotating this cylinder at a constant angular velocity of omega. The liquid will rise at the ends and fall at the center. So at the end the liquid will rise from O to B. At the center it falls from O to A. Now let Y, look at this figure, this is the rise in fluid at the ends. Now X, the fall of fluid at the center, OO, okay, from OO. Then the volume of liquid is equal to volume of cylinder up to level BB minus volume of paraboloid. Now I will go back to the figure. Now look at this. I said this is the parabola. Okay. Now if I want the volume of this fluid present between this B, A, B and this portion, what I am going to do is I am going to find the volume corresponding to this, and from that I am going to subtract this portion. I repeat, if I want to find the volume of fluid when the cylinder is rotating, in that case what I am going to do is I am going to find the volume of the cylinder corresponding to this BB, and then I am going to subtract this parabola volume from this original volume. That is what I mentioned in the next year. Look at this. This is volume of the cylinder up to level BB minus volume of the paraboloid. Now this is given by pi r square into height of liquid up to level BB minus what is the volume of paraboloid, that is given by pi r square into height of the paraboloid. Now come over here. Height of liquid up to level BB is given by, again go back to the figure. Look at this. Right now I am talking about this height. This height is equal to y plus x plus h. I repeat, from B to this base of the cylinder it is h plus x plus y. That is the height of this level BB from the base of the cylinder. The next one, so I am talking about the height of the paraboloid. What is the height of the paraboloid? Height of the paraboloid is equal to y plus x. Height of the paraboloid is given by y plus x. Look at this. That is what I mentioned here. Pi r square into h plus x plus y minus. So the volume of the paraboloid is given by pi r square by 2 into the vertical height, that is x plus y or y plus x. Okay. If you simplify this, you are going to get pi r square h plus pi r square by 2 into x plus y. I repeat, once you substitute these values, if you simplify this, what I did in the next step, I multiply this pi r square into h, and this is x plus y. On the right hand side also you have x plus y. So regroup these terms. That is what I did here. Pi r squared h plus pi r square into x plus y minus pi r square by 2 into x plus y. Now, so this pi r square h plus pi r square by 2 into x plus y, that is, if you simplify this, you are going to get this pi r square by 2 into x plus y. Call this as equation 2. Remember, you have equation 1, you have equation 2. Now equating 1 and 2, okay, what is equation 1? Remember, equation 1 is the volume of the liquid when the fluid is not rotating. Okay, what is 2? So volume 2, equation 2 represents the volume of the liquid when the fluid is rotating. So if you equate this equation 1 and 2, you are going to get this pi r square into h plus x is equal to substitute this equation 2 on the right hand side, and if you simplify this, you are going to get this pi r square by 2 into x, that is equal to pi r square by 2 into y. I repeat, if you equate equation 1 and 2 and on simplification, you are going to get this pi r square by 2 into x, that is equal to pi r square by 2 into y. Remember, so this and this gets cancelled, you left with this x is equal to y. What is x? Fall of liquid. What is y? Rise of liquid. Rise of liquid at the ends, fall of liquid at the center. So what it says, your OA is equal to OB. In other words, whenever there is a vortex flow, the rise of liquid at the ends is equal to fall of liquid at the center. I hope it is clear. With that, let us solve one or two problems on this vortex flow. Let us start with the first problem. An open circular tank of 20 centimeter diameter and 100 centimeter long contains water up to a height of 60 centimeter. The tank is rotated about its vertical axis at 300 rpm. Find the depth of the parabola formed at the free surface of water. Basically what you need to find? You need to find what is the value of x plus y. Okay. So a open circular tank 20 centimeter diameter, 100 centimeter long, contains water up to a height of 60 centimeter. The initial depth of water in the tank is 60 centimeter before start rotating. Now the tank is rotated about its vertical axis at a speed of, in this case n is given, n is 300 rpm. Find the depth of parabola formed at the free surface of water. Let us see how to solve this problem. Solution: dia of the cylinder 20 centimeter. Now what is the radius of the cylinder? So dia divided by 2, that is radius is equal to 10 centimeter. Height of liquid capital H is equal to 60 centimeter. If you refer to the earlier figure what I gave, it is small h plus x. So that is the initial level. In this case I replace that small h plus x by capital H, therefore that becomes 60 centimeter. Speed n is equal to 300 rpm. Now I know the relation between this tangential velocity, angular velocity and speed. In the next step I consider a relation between angular velocity and speed. Okay, angular velocity is given by 2 pi n by 60. Okay. Now this omega is equal to 2 pi n by 60, therefore substitute the value. So 2 pi is constant, n is given in the problem 300 divided by 60, you are going to get the angular velocity. Angular velocity has 31.41 radians per second. Now let the depth of parabola be z. Okay. So what is z? In the earlier notation what I gave, it is the rise plus the fall, that is x plus y. So in this case that x plus y are represented as capital Z. Now we derived one more relation. What is that relation? Z is equal to omega square r2 square divided by 2g. I repeat. So this z is equal to omega square r2 square divided by 2g. That's what I showed at the beginning of this class. Okay, this z is nothing but the depth of the parabola. Depth of the parabola is given by w square omega square r2 square divided by 2g. Now in this case what is the value of r? R2, the value of r2 is equal to capital R. Now just now you calculated the value of omega. Omega is 31.41. So 31.41 square. Now in this case the radius given in the problem 10 centimeter, therefore 10 square divided by 2 into 981. So there is a slight correction here, kindly. This is 981. So if you simplify this, you are going to get the height of the parabola as 50.28 centimeter. Okay, I repeat. So you need to remember this formula. You have all the required values, substitute the values and find the value of z. What is this capital value? Capital Z? Capital Z is the total depth of the parabola. What is the total depth of parabola? It is the rise of fluid plus the fall in fluid, that is x plus y. My x plus y is equal to capital Z, that is equal to omega square r2 square divided by 2g. Substitute the values and find the value of z. In this case the value of z works out to be 50.28 centimeter. That is a simple problem. Let us make little complicated things or add little masala in the problem. So let us go read this problem. An open circular cylinder of 15 centimeter diameter and 100 centimeter long contains water up to a height of 80 centimeter. The initial height of water is 80 centimeter. Find the maximum speed at which the cylinder is to be rotated about its vertical axis so that no water spills. Read this problem once again. An open circular cylinder of 15 centimeter diameter and 100 centimeter long contains water up to a height of 80 centimeter. Find the maximum speed. You need to find the value of n at which the cylinder is to be rotated about its vertical axis so that no water spills. Okay, how to solve this problem? Let us see how to do that. Dia of the cylinder 15 centimeter. You need radius, therefore radius is equal to 15 divided by 2, 7.5 centimeter. Length of the cylinder L is equal to 100 centimeter. Initial height of water is 80 centimeter. Now you need to rotate this cylinder in such a way that the rise in level should not cross this 100 centimeter. Let the cylinder is rotated at an angular speed of omega radians per second. When the water is about to spill, then using the relation what we derived in the earlier problem, we showed that rise of liquid at ends is equal to fall of liquid at the center. So we showed that x is equal to y or y is equal to x. Okay, but rise of liquid at ends, what is the maximum height to which you are going to rise this liquid? Remember, the length of the cylinder is 100. I said the moment once it crosses 100, there is a spill. Therefore, the maximum height to which you can allow the fluid to rise or water to rise is 100. That is what I put in the next step. But rise of liquid at ends is equal to total length of the cylinder minus the initial length. That is, total length is 100 and the initial level is 80, therefore it is 20 centimeter. That is, you can rise the fall of liquid at the center is 20 centimeter or the rise of liquid at the ends is 20 centimeter. Now, if you know this, there is nothing in the problem. So, what is the height of the parabola? Height of the parabola, we represent this as capital Z. Capital Z is equal to x plus y. What is x? X is the fall of water at the center. Y is the rise of water at the edge. What is the fall? Fall is 20 centimeter. What is the rise? 20 centimeter. What is the height of the parabola? Therefore, 20 plus 20, it is 40 centimeter. But I know one more relation. What is that relation? Relation between the depth of parabola and the angular velocity. So, depth of parabola is equal to omega square into r2 square divided by 2g. Now, you know all the values except this omega. So, find the value of omega. So, in this case, omega works out to be 37.25 radians per second. Okay. Now, once you find the value of omega, now there is a relation between this omega and speed. What is that relation? Omega is equal to 2 pi n by 60. Okay. Now, n is, so you need to find the value of n. Therefore, n is equal to 60 into omega. Omega just now you calculated, it is 37.235 radians per second divided by 2 pi, which is constant. Substitute these values and if you find the value of n, n works out to be 356.66 rpm. I repeat, n is equal to 356.66 rpm. What is the conclusion? The conclusion is, if I rotate the cylinder at a speed of 356 rpm, okay, the rise of fluid at the ends will not cross 100 centimeter or the length of the cylinder. So, what is the crux behind this problem? The crux behind this problem is to remember this. So, that is, the rise of liquid at the ends is equal to fall of liquid at the center. What is the maximum height you can allow this fluid to rise? That is equal to the length of the cylinder. The length of the cylinder is 100 centimeter and the initial height is 80 centimeter. Therefore, 100 minus 80, that is 20 centimeter. 20 centimeter height you can allow rise and 20 centimeter you can allow it to fall. Okay. So, with that we can solve this type of problem. I hope these three problems are sufficient to solve any type of problem on this vortex flow, whether it is free vortex or forced vortex. So, with that I will stop this vortex flow. The next and the foremost important chapter for a civil engineer is this orifice and mouthpiece and notches and wires. Orifice and mouthpieces are extensively used, or whatever the topics we are going to cover from here afterwards, you are going to see this extensive use in the field. Let us start with the first one, orifices. Again, remember, this orifice mouthpiece is again based on Bernoulli's equation. I repeat, orifice mouthpiece is based on Bernoulli's equation. So, where we are going to use this equation, Bernoulli's equation or energy equation in these cases, as we go further and further, you yourself will realize the importance of Bernoulli's equation in these devices. Let us start with this orifice. Orifice is a small opening. Kindly recall, I already introduced an orifice to you. Where did I introduce this orifice? Remember? So, once we derived this Bernoulli's equation, applications of Venturi Bernoulli's equation, we mentioned about three devices. One is Venturi meter, the second one is orifice meter, the third one is pitot tube. When I was talking about the orifice meter, I said it is a circular plate at the center of which there is an opening. Okay, this opening is called an orifice. The same thing I gave it here. If you look at the definition, orifice is an opening in a vessel through which liquid flows out is known as orifice. Basically, in other words, if you make an hole or an opening in a plate, the hole behaves as an orifice. Okay. Now, what is the condition? Condition is very important. Look at the second sentence. The hole or opening is called the orifice so long as the level of liquid on the upstream side is above the top of the orifice. Very, very important. Okay. If you consider a circular orifice, you have a bottom edge, you have a top edge. Okay. Now, see to it that the water level is always above the top edge of the orifice. Now, where do you use this orifice? Orifice is extensively used to measure the discharge. I repeat, orifice is extensively used to measure the discharge. Remember, Venturi meter is used to measure the discharge in a pipeline. Orifice meter is also used to measure the discharge. Orifice meter, then orifice is also used to measure the discharge. Now, where do you provide this orifice? Where do you provide an opening? So, most of the time you are going to see the orifice on the side of the tank or at the bottom of the tank. But the opening at the side of the tank is very common. I repeat, the opening you are going to provide either at the side of the tank or at the bottom of the tank. But in most of the cases, you are going to see this orifice on the side of the tank. Then, what are the types of orifices? So, there are different types of orifices based on size, shape, nature of discharge. Okay. So, let us see what is the classification. Now, according to size, there are two types of orifice. One is a small orifice, next one is a large orifice. Then, depending on the shape, we have a circular orifice, very common. Then we have a rectangular orifice, and the third one is a triangular orifice. Again, I repeat, depending on the shape, we have a circular orifice, a rectangular orifice, and a triangular orifice. Then, the next classification is based on the edge. Okay, what is this edge? I will come to this. So, based on the edge, we have sharp edge orifice. Next one is bell mouth orifice. It is bell mouthed orifice. Okay. Now, kindly concentrate on the figures what I gave here. Okay. If you look at this figure, this is the upstream edge. I mean, if you consider the thickness of the tank. Okay. Now, it is a very sharp edge. In other words, whenever I provide a sharp edge, the fluid in contact with the sharp edge is minimum, or with the in contact with the container is minimum. So, fluid comes, it touches the tip and moves away. So, that is in case of a sharp edge orifice. Whereas, in case of a bell mouth orifice, look at this. This is the upstream edge, this is the downstream edge. There is a smooth outlet here. So, water comes. So, all along this flow, this water or the fluid is in contact with the edge. I repeat once again, in case of a sharp edge, so the contact of fluid with the edge is very minimal. Once the fluid comes and strikes this edge, it deflects away from the edge. Whereas, when I am talking about a bell mouth orifice, look at this, this is a smooth edge. Now, all along from the upstream edge to the downstream edge, the fluid is in contact with the edge. This is called the bell mouthed orifice, and this is called the sharp edge orifice. Then, depending on the nature of discharge, we have three types of orifices. One is, we talk about orifice discharging free. The second one is fully submerged orifice. The second one is partially submerged orifice. Now, concentrate on the figure what I gave here. Kindly excuse me because this problem is not very clear. Now, the circle what you see is the dia of the orifice. Okay, again I repeat, the circle what you see here is the dia of this orifice. There is a tank, on the side of the tank there is an orifice. Now, water or the fluid from this tank, it is discharging free. Now, what I showed here, this is the level of water on the downstream side. Now this is the upstream side, this is the downstream side. Now the level of water on the downstream side is much below the bottom edge of the orifice. I repeat, in the first case, when I say the orifice is discharging free, the level of water on the downstream side is much below the bottom edge of the orifice. Then this is called orifice discharging free. Okay, so when we call it as a submerged orifice, suppose on the other hand, rather than the water level here, if the water level is above the top edge of this orifice, remember this is the bottom edge, this is the top edge. If this water level is above the top edge of the orifice, this is completely submerged. Remember, on the upstream side you have water, on the downstream side also up to this level you have water. In other words, this orifice is completely submerged. Then we call it as a fully submerged orifice. Clear? Now again I repeat, if the water level or the fluid level on the downstream side is much below the bottom edge of the orifice behaves as a discharging free orifice. If the water level on the downstream side is above the top edge of the orifice behaves as a fully submerged orifice. Now, if the level of water or fluid is between the top edge and the bottom edge, maybe somewhere here, then this orifice behaves as a partial submerged orifice. Clear? Now this is a discharging free, this is completely submerged. If the level of water or fluid is between this top edge and the bottom edge, then this behaves as a partially submerged orifice. This is a classification of different types of orifices. I hope it is clear. Then kindly recall, when we derived a discharge equation for a orifice meter, I introduced this term Vena Contracta. Now let us see what is this Vena Contracta, when it is going to form. Okay. Now look at this, kindly concentrate on this figure. Now in the last class, remember I said the momentum of the flowing fluid cannot be changed abruptly. What do you mean by this? Suppose if the fluid is flowing in the x direction, suddenly if you provide a 90-degree turn, okay, from x to suddenly y, okay, then that cannot happen. For example, if you construct a channel, okay, so in the x direction, suddenly if you change the direction to y direction, if you allow water to flow in the channel, after 15 days or 20 days if you go and see, okay, it takes its own form. So initially it was perfect 90-degree turn. After some time you are going to see a smooth transition from x direction to y direction. At that intersection, one side there is a erosion and the other side there is what is known as deposition. You are going to study this in irrigation engineering. Now for this moment, please remember the momentum of the flowing fluid cannot be changed abruptly. With that concept, let us see what is this Vena Contracta when it is going to form. Consider an orifice pitted with a tank. The liquid particles, in order to flow out through the orifice, move towards the orifice. Remember, this is the tank, okay. So assuming that this is a big tank, so you have fluid up to this level. The moment once you provide this orifice, so this fluid particle starts moving away from this orifice. That is what I mentioned in the first paragraph. A few of the particles first move downwards, then take a turn to enter into the orifice and finally flow through it. What do you mean by that? Suppose if this is another side and this is the bottom side, the fluid particles slides smoothly along the boundary and finally, so the fluid particles present attached to this boundary, it moves along the boundary, it flows at the bottom and finally moves along this boundary and gets out of this orifice. It may be noted that the liquid particles lose some energy while taking the turn to enter into the orifice. I repeat, it may be noted that the liquid particles lose some energy while taking the turn. Remember, this is this direction and this is this direction because of the presence of the orifice. Okay, so you are changing the momentum or the direction of these fluid particles. Okay, so when you do this, so the fluid particles loses some energy. Now it can be observed that the jet after leaving the orifice gets contracted. That's what I mentioned here. This is the point where the jet gets contracted. The maximum contraction takes place at a section slightly on the downstream side of the orifice. Okay, it is not exactly at this point. This is going to happen slightly downstream side of the orifice, where the jet is more or less horizontal. If you look at this figure, so I showed this almost horizontal. Now, this section is called Vena Contracta and is represented as CC. Okay, so this is called the Vena Contracta, and from here afterwards we are going to use this Vena Contracta to a great extent in the later derivations and also in problems. Then we will introduce this hydraulic coefficients. Remember, when I was talking about Venturi meter, I was talking about orifice meter, I was talking about pitot tube. We introduce 3 hydraulic coefficients. What are those? In the first case, first instant, I introduce coefficient of discharge represented as CD, and it is defined as the ratio of actual discharge to the theoretical discharge. If you recall, I said when I am talking about actual discharge, I am considering the losses that are happening in a fluid flow. When I am talking about the theoretical discharge applies to a ideal fluid where we do not have any losses. That is why I said actual discharge is always less than the theoretical discharge. Now, if at all if you want actual discharge, knowing the theoretical discharge, you need to multiply this theoretical discharge by this coefficient of discharge, CD. I said this coefficient of discharge is always less than or equal to 1. In other words, actual discharge is equal to coefficient of discharge into theoretical discharge. That is in the first case. This is we defined when I was talking about Venturi meter. Then the second one is this coefficient of contraction. How did we define this coefficient of contraction? It is the area of the jet at Vena Contracta to the area of the orifice. I repeat, coefficient of contraction is A naught divided by AO. What is this A naught? A naught is area of the jet at Vena Contracta. AO or A, simply put it as A, is the area of the orifice. Okay, that we call it as coefficient of contraction. We also define this coefficient of velocity, CV. What is this coefficient of velocity? Coefficient of velocity is defined as the ratio of actual velocity divided by theoretical velocity, V actual divided by V theoretical. Now, in the pitot tube, we derived an equation for this velocity, V is equal to root of 2gh. That equation we call it as what is known as Torricelli's equation. Remember, Torricelli's equation is a theoretical velocity, V is equal to root of 2gh. Now, if you multiply that by coefficient of velocity, you are going to get the actual velocity. In addition to these 3 hydraulic coefficients, there is another hydraulic coefficient called the coefficient of resistance. Let us see this in the next slide. First one, this is what I mentioned. CC is the area of jet at Vena Contracta to the area of the orifice. Now look at the last sentence. The average value of CC is 0.64. Okay. Now kindly remember these values. These values will help you a lot when you are doing the experiments in your laboratory. Come to the next one, coefficient of velocity. Coefficient of velocity is the ratio of actual velocity of the jet at Vena Contracta to the theoretical velocity. Okay. Now I said this theoretical velocity is given by root of 2gh and h is the head of water at Vena Contracta. This is what I mentioned here. CV is equal to actual velocity of the jet at Vena Contracta to the theoretical velocity of the jet. Then the coefficient of discharge. Sir, you skipped a couple of points. This couple of points I already mentioned to you. The difference between velocities is due to friction of the pipe, friction of the orifice. I said whenever I am talking about theoretical discharge, I am not considering any losses. This, if you remember, that will be more than enough. Coefficient of discharge, CD is equal to actual discharge divided by theoretical discharge. Then another important thing you need to remember is the relation between coefficient of discharge, coefficient of velocity, coefficient of contraction. Now actual discharge is equal to, by continuity equation, what is this continuity equation? Q is equal to A into V. Now actual discharge is equal to actual velocity into actual area. What is theoretical discharge? Theoretical discharge is equal to theoretical velocity into theoretical area. Now, actual velocity divided by theoretical velocity is nothing but CV. Actual area divided by theoretical area is nothing but CC. Then what is the relation between this CD, CC and CV? So, CD is equal to CC into CV. Okay. Now, this relation is very important, because finding the exact location where this Vena Contracta is formed is very difficult. I repeat, finding the exact location where the Vena Contracta is formed is very difficult. Whereas, finding the value of CD, finding the value of CV in the laboratory is very easy. I am going to discuss this in the next class. Okay, I repeat, finding the value of CD and finding the value of CV is very easy. Knowing these two values, CC can be easily determined. How you are going to find the CC? CC is equal to CD divided by CV. So in that aspect, this relation CD is equal to CV into CC helps a lot in getting the relation between three hydraulic coefficients. Now, the coefficient of discharge varies from 0.6 to 0.64. Okay, most of the time if you go to your laboratory, in my case, okay, the coefficient of discharge for a orifice in our laboratory is around 0.5 to 0.51. Okay, maybe you try in your laboratory. So if the coefficient of discharge is more, okay, what the conclusion? The conclusion is your actual discharge is close to your theoretical discharge. That is, losses are minimum. Come to the last one, coefficient of resistance. The ratio of loss of head in the orifice to the head of water available at the exit of the orifice is known as coefficient of resistance. Again, I will define this. The ratio of loss of head in the orifice to the head of water available at the exit of the orifice is known as coefficient of resistance. Sir, do we use this coefficient of resistance? Very rarely we are going to use this relation. Most of the time, as a civil engineer, you are going to use the three hydraulic coefficients what we mentioned earlier, CD, CC and CV. Okay, so this CR, coefficient of resistance, is given by loss of head in the orifice divided by head of water. Okay, with this I conclude this session. So we started with the problems on this, the relation between velocity and radius in case of a forced vortex. Then we showed that the rise of fluid at the edge is equal to fall of fluid at the center. We derived we solved couple of problems on this forced vortex. Then we moved on to this orifice and mouthpiece. I said orifice and mouthpiece, the basic principle of this orifice and mouthpiece is also based on Bernoulli's equation. Then we studied about the different types of orifices. Then we discussed about this different hydraulic coefficients. So let me come out with the equation for this sharp edge orifice in the next class. Thank you.